All right, now we're going to get into compression design. We've gone through the theory behind the compression design, and now we're going to talk about how we're actually going to design columns and other members that are in compression using the manual. Right, we're going to focus on non-slender compression and assuming we're going to look at a lot of the times flexural buckling will control the effect of slender cross-sectional elements, effective length factors, and how to do that in a frame. And then we're going to do a bunch of examples. I'm going to summarize the method and do some examples. So, as we've talked about previously, the local buckling is in, if we determine whether or not local buckling needs to be accounted for, is in Chapter B, particularly Section B 4.1, and you're going to look at Table B 4.1a. This is on page 16.1-17. If you go look at the manual, let's see. Oh, goodness. If you go look at the manual, let's see. You want to make sure, and there's some different tables. We want to do table 4.1 because it says axial compression. If you look at the next page, 4.1b, right, that was 4.1a. This one is about flexure. So don't look at that one, look at 4.1a because we're talking about things that are in compression. And so you calculate your width to thickness ratio, compare it to a limiting width to thickness ratio, and determine whether or not you have slender elements, which means if you have a slender element, you're going to have to account for some local buckling, and it's some different design equations. We're actually not going to do too many examples or any involving slender elements, but I want you to know what it's called, why it's there, and how to determine if you need to account for it. So let's see. So that's Chapter B. Chapter E, right, is all about compression, and we'll go through it, but that starts on page 16.1-33. We're going to focus, like I said, there's the general provisions where we have our phi factor, a table that we're going to use, the effective length factors, and then we're going to focus on flexural buckling without slender elements. So that's where we are in the spec, right? This is all the specification. The design charts and tables this time, look at your little tab that says call. And that's your part 4, which gives you design tables that are based on the spec, right? If you have this certain member and I design it certain ways according to the specification, this is my design strength and other information. So part 4, that's the design tables. Those are just applications of the design equations in the spec. So let's start with, right, section B 4.1, we just saw like table B 4.1a, And that's where you compare your width to thickness ratio, lambda, to some value, lambda r, and if lambda is greater than lambda r, you have slender elements. Sorry, that's a terrible looking thing. It looks like a witch's broom or something. There you go. Alright, that's slender elements. This local buckling is covered in the spec. Those are the design equations accounting for it in section E7. Right. And then this lovely little sentence right here. Many rolled W-shaped sections are dimensioned so that full global buckling or global criteria controls, meaning local buckling does not control. Right? They would rather fail globally, as in the entire section fail in flexural buckling or torsional buckling or flexural torsional buckling, than have a local instance of buckling. So let's see, E1, if we go to chapter E, our very first section, we're on page 16.1-33. This is where the biggest thing is that our phi for compression is 0.9. Right, oh, okay, hold on. Erase that. Compressive design strength is phi for compression times our nominal compressive strength, where phi c equals 0.9. Pn is our nominal compressive design strength, or compressive strength. And we're going to have some equations on how to calculate that. Similar to tension, when we had to calculate, our nominal strength was either Fy times the Ag or Fu times the Ae. There are going to be some equations. They're not quite as simple as those, but they're in the next couple sections. There's also this lovely user note. It is called Table User Note E1.1, and this table I'm going to show you in a minute gives limit states that apply based on your section shape, your cross-sectional shape, and if you have slender elements. So we have our 4 limit states that we talked about that can happen in compression: flexural buckling, torsional buckling, flexural torsional buckling, and local buckling. And it has been determined which limit states, certain limit states might not apply to actually all the sections, because torsional buckling, you're probably not going to have a torsional buckling in flexural torsional buckling. Anyway, there are certain shapes that just aren't going to lend themselves to certain types of buckling, is what I'm trying to say. So if we look at that, let's see. Here is the user note. It's on page 16.1-34. Hopefully it's not, hopefully there's not much differences. So if you look at the first one here, the first one is this is a symmetric I-beam. So any of your rolled W shapes, right? You need to check, if it doesn't have slender elements, you only need to check flexural buckling and torsional buckling. That's what those are. FB is flexural buckling, TB is torsional buckling. It says it right down here at the bottom. What do you not have to check? Flexural torsional buckling. So, and those you can find, flexural buckling is in section E3, torsional buckling is in section E4. If your I-beam does have slender elements, now you have to go to E7 to do all of that, to flex local buckling, flexural buckling, and torsional buckling. And it's all in section E7. You're not going to use section E3 or E4. So, and then you could go on down the list. This is a channel and a non-symmetric I-beam, right? Either it has 2 different flange sizes, or a really thick flange and a not as thick flange. I guess it's a doubly symmetric. That's what I'm looking for. Doubly symmetric. It's symmetric about the x-axis and the y-axis. This is singly symmetric shapes. Right here's a rectangular HSS, hollow steel section, round HSS. This is a WT or an ST. It's a T, right? Here we have a double angle. And this is a single angle. And then this is not a hollow, right? A bar or a plate or something like that. and unsymmetrical shapes other than single angles. We're gonna stick to like, you know, those, maybe that. I don't know. No, we're not gonna get into that. So, let's see. So that is how you can use this note. If you're like, I wonder which limit states apply, you can go look at your cross section and it'll tell you. Right? Whereas before, when we were doing tension, we always had to check yielding and rupture. Now it'd be like if they said, rupture's never going to apply to this certain section, so you only have to check yielding. Not true, but it would be for that. Like there's 4 limit states, but you don't have to check all of them, is what this user note table is telling you. So let's see. So that is that user note. It is helpful. Finally, section E2, we have our effective length and how to calculate it. Effective length, ugh. Is denoted by the symbol LC, or effective length and compression. Is denoted by LC, and it equals our K factor times, remember our K factor is to account for different end conditions other than pin-pin. So let's see, K is our effective length factor. And L is our unbraced length. Of the compression member. K is based on, you can figure out your K. It's based on your end conditions. And this is where you're going to want to put a tab. I didn't talk about it previously because you guys wouldn't have known what I was talking about. But we're going to go to a table back in the commentary. Table C-A 7.1. It is on page 16.1-570. So flip to your manual right now. Go look at it. I'm going to bring it up in a second. So this is a tab that you're going to want to put. You're going to want to put on your book. So 16.1-570. Let's hope all these numbers are still the same. Okay. 16.1-570. Remember, I'm looking at a different edition, so it's a different page number. Okay. So here we have, I think we did this previously, but in the theory, but right, we have a fixed. Your theoretical K value is 0.5 because it's based off of how many, the length compared to actually having a pin, right? This would be our pin buckled. So you can get, so the length for a pin would be half of the whole length for a fix. Use the, and it goes on and on, right? Fixed, pin fixed, fixed free, tells you what they are down here. Pin, that's our one, that's our Euler buckling. Let's see, fixed free, and then fixed free, but with the, or no, pin free. Right, actually this is translation free, this is rotation and translation free. So you're going to go back here when you say, I think I have these end conditions, and use the recommended values. Okay? These are the theoretical ones. But since design isn't perfect, we're going to use the recommended ones. So again, put a tab here. You will need this. Use recommended design values. See if I can write recommended better. Recommended. So that's where your K factors are located. Now if we go back to chapter E, we're still in E2. They also talk about a slenderness ratio. Again, now we're talking about KL over R. And remember that determined if we had it helps determine buckling, but also inelastic versus elastic buckling. So, or LC over R. Whenever you see LC, it's K times L. Similar to tension, this is actually not this is a recommendation for serviceability. It's not a requirement. Obviously, the slenderness ratio has to deal with a member's design strength, so it's going to have more of an effect than it ever did on tension, but the slenderness ratio, there is a recommendation for serviceability. And it says KL over R less than 200, where R is again your radius of gyration. Now here's a big note, and we're going to talk about it later. Note, your unbraced length L may be different in different directions. And I'm going to show an example of that in the next slide. Therefore, your R, use R corresponding to L. Okay, I'm going to show you what that means in a minute. This is where a lot of people got kind of confused, especially when it comes to using the design tables. So I hope you all can figure it out. And if you have any questions, please let me know. So what do I mean by different directions? Well, in our cross section, we have a strong plane. Like if we're looking at this, we're looking at an I-beam, right? We have our XX and our YY axis, our XX axis and our YY axis. Strong plane XX, weak plane YY. I want you to look at this first one. This is over here, sorry. And these two right here, strong plane, this is what buckling about strong axis looks like, where you would use your moment of inertia Ix and your radius of gyration Rx. Then your weak axis, this is what it looks like. Buckling, right? You see it's in this one, it's in the strong one, in the strong plane, it's kind of easy to see it's bending about this y-axis, or I'm sorry, this x-axis, right? Here oh, don't do that. I meant to draw a curve. Right, these are the flanges. Let's see. This is the axis. And the flanges. It keeps straightening out my line. Right, this is the flange, this is the other flange. So you see how it is buckling or bending, flexural buckling, right? I was talking about bending about the strong axis. Whereas if we're talking about the weak plane, this center line right here, corresponding to the YY axis, also happens to be the web. So if we're looking at this weak plane in elevation, what we're looking at is straight on, we're looking at at one of the flanges, right? It might be this one, I don't know. That's an entire flange. The other flange is behind it. So it's buckling about this weak axis. Okay? So, this is where, if I want you to look at this top section right here, and this is a brace, which is like a support. Is this support preventing bending about the y-axis or the x-axis? I want you to think about it for a minute. This brace is preventing buckling or bending about the y-axis, right? It's like if I can draw something. Think. Yeah. Right, weak axis buckling. I wonder if I could draw like a 3D. That would be great, wouldn't it be? Looks like that, right? So this brace, I don't know if that's easy to tell or not. Right, if this is my web, and then my flange is on top of it. It's kind of buckling about that y-axis. So if I put a brace, like let's say there's a brace here and a brace here, if I put a brace here, it would be perpendicular to the web. So I could have a brace preventing buckling about the y-axis. On the other hand, here my brace is parallel to my web, and it's perpendicular to my flanges. So in this case, we're in strong axis buckling. It'd be like if you put like a brace, like right here. There's the top and there's the bottom. Look like that. How would that look? Now, my little thing, alright, is, there's my web. There's my other, this is kind of harder to draw. That's my other flange, that looks terrible. So in this case, right, it's preventing, that's the axis that it's preventing. In this case, it's preventing this axis and the other axis. So this brace So that's an example of how it can be braced against buckling. And sometimes it might be braced because usually y-axis, generally the radius of gyration in the weak axis is less, and therefore it is more slender and more likely to buckle in the weak axis. So maybe they'll put bracing in for the weak axis buckling. And now you have different brace lengths for your x-axis and your y-axis, and maybe now strong axis buckling might occur before weak axis buckling. Okay. I just wanted to hopefully have some more visuals about how that happens. So let's see. So that's all about the effective length and the slenderness ratio. Section 3 is now where we're actually going to start calculating design strengths, right? So section 3 focuses on flexural buckling of members with slender elements. So flexural buckling only. If a section you can tell from the user note, right? If a section does not contain slender elements, that means we don't have to account for local buckling, right? And is doubly symmetric, then this is the section for you to calculate flexural buckling. And flexural buckling is global buckling, like Euler buckling, it's bending. So if a section does not contain slender elements and is doubly symmetric, then flexural buckling, such as the type determined in this section, is most likely the potential failure mode. That means it's not going to have any local buckling. It's not going to have any torsional buckling, probably. And how we calculate our nominal compressive strength, Pn, is equal to a critical stress times our gross cross-sectional area. So the rest of the section tells us how to calculate that critical stress, and it is based off of your slenderness ratio. If you go back and look at our notes from compression theory, you might recall that the more slender a cross section is, the higher its slenderness ratio, then the more likely it is going to buckle elastically, meaning there won't be any yielding within the cross section prior to buckling. It's all going to stay within the elastic range. If it has a low slenderness ratio, it will have yielding within the cross section prior to buckling, which is a result, as we talked about, of residual stresses. And it is inelastic, so therefore it's inelastic buckling. So the first one, right, LC over R, we're going to compare, this is my slenderness ratio. We're going to compare, right, that's KL over R, my slenderness ratio, and we're going to compare it to 4.71 square root E over Fy. If you remember checking about local buckling, it was a constant, some type of number, times the square root of E over Fy. Now we're looking at it on a global scale. So if I have a small slenderness ratio, if it's less than this critical slenderness ratio, then we have inelastic buckling. Ugh. And I calculate my critical stress using this equation. And if I have a high slenderness ratio, then I'm more likely to buckle before I have any yielding. So I have elastic buckling. This, if I have elastic buckling, I use my stress associated with Euler buckling stress, that's Fe. That's my stress associated with perfect, wonderful Euler elastic buckling. And then I'm going to reduce it, right? There's a little bit of a reduction factor based off of research. And if I have inelastic buckling, now it's this ratio, this equation was developed by people doing decades and decades and decades of research to find that equation and to fine tune that equation. All right, this is my Euler buckling stress, pi squared over my slenderness ratio squared times E. Okay? If you want to, in your manual, I have done this in mine. If you want to, in your manual, go to section E3. Go to section E3, right? If you have a low slenderness ratio, and you can write inelastic buckling or inelastic. If you are higher slenderness ratio, you have elastic buckling. I have seriously written this in my manual to remind myself. So you may go ahead and write that if you would like. So if I go back to my notes here, these curves or these equations I'm going to recall back to compression theory where I drew the variation of my stress with my slenderness ratio and how I had elastic over here and there was some point where it changed to inelastic buckling, and now, whereas before, if this is my Euler buckling stress, then this is my stress. Now I've replaced that E with our tangent modulus. To get my curve corresponding to inelastic buckling, because I have this tangent, elastic modulus that incorporates yielding within the cross section. And that change also corresponds to my difference where I have residual stresses that are due to that uneven cooling. So this was my equation, or this is my chart that we talked about in compression theory. Now, if I look at the same chart of the using the equations, right? This is equation. This is the critical stress for elastic buckling. It is equation E3-3. This is for inelastic buckling, E3-2. And you can see how that blue line compares to the theoretical, right? We've reduced our stress ever so slightly. Because of testing, right? It's not perfect. And let's see, we have now, this is my, right, my slenderness ratio. That differentiates between inelastic and elastic buckling. caused by the residual stresses leading to yielding in the cross section before buckling of the entire member. You can say for elastic, the section remains elastic, and yields at the same time. Inelastic, you have yielding prior to full buckling of the cross section. So that is the what we'll be focusing on is section E3. We're not going to get into E4 or E7 with local buckling. We're going to focus on just this one section. But I want you to know that there are other limit states. We're just going to focus on flexural buckling of doubly symmetric sections with non-slender elements. So that's the spec. That's what we're going to look at in the spec. Now, how about we look at part 4, where our design tables that are applications of the spec. The good sections to know about, we have table 4-14, which has your phi critical stress, right? We just talked about our critical stress here. Now you can figure out the critical stress based on the slenderness ratio. And it's useful for all shapes, right? If you know, right, let's see, our design equation was phi c pn equals phi c critical stress ag. I just remembered that, yeah. So here we have the critical stress part. And so it can be useful in helping to select a cross section or calculating your design strength. So what does that one look like? See, it's useful for all shapes. It is not specific to any type of shape. And your larger slenderness ratio controls. So let's see what that looks like. You'll see what these charts mean when we get to beams. They look super scary, but they're not. Let's see. Okay, table 4-14. It starts on page 4-229. So let's see. It starts on page 4-229. So we're up in the first 2/3, right, where we have all of our design tables, which are just calculations from the spec. The spec rules everything. They just decided to make it a little bit easier on you. So let's see, 229. Oh, jeez. Ooh, look at that. slightly different page numbers, so don't look at it. Oh, and that's a totally different table. Oh no, please tell me it's not a different. I never had the 14th edition, so I don't know. I think I had the 13th edition for when I took the P. So this is table 4-14 in the 15th edition. There it is. Available critical stress 44322. Oh my. Okay. So like 7, 4, something like that. Okay. So again, it's table 4-14 in the 15th edition. I'm looking. Yeah, so that's 4-13. Okay. 4-14. So I don't even know if these numbers are right. Who knows? Stuff could have changed. Maybe not. So if you have a yield stress of different values, right? Usually 50 KSI for our A992, 36 for our A36 steel. You go and you look at a slenderness ratio, and this is the this is our, remember we're sticking with LRFD, we're not doing any of that ASD stuff. That's your phi critical for a given slenderness ratio. If you have a slenderness ratio that is 12.2, you can interpolate. Now granted, that's not 32.2, 32.1, that's not that different. But we're going to learn all about interpolation, right? Again, phi is 0.9, this is our critical stress, and it goes through a bunch of different slenderness ratios. What's the highest that it gets to? 200, because that's how high they want you to stay, right? It's a smart manual, somebody thought that through. Right? Because that's my limiting slenderness ratio is 200. So that is table 4-14, which is a slightly different number in the old 14th edition. Tables 4.1 table 4-1 to 4-12. This is similar to the tension design tables. It is the available, it is look up a shape, right? I don't know where this even starts. It starts at the very beginning, a very good place to start. This is actually going to have different different FYs. So let's see, what do we need to know? So these are VCPN by shape and FY and our effective length in the Y direction. These tables assume that weak axis buckling controls. If weak axis buckling is not going to control, you can change how this, you can use these tables still, but you have to do a little bit of calculations, okay? So make sure you have the right FY at the top. I'm saying that because, let's see. Because if you look at the notes, oh, they're not in there. Is that true? Well, if you look in the 15th edition, see in the 13th and the 14th edition, it always assumed an FY. If you look in the 15th edition, you have table 4.1A, 4.1B, and 4.1C with different FYs. So be sure and look at that. Make sure you are looking at right. For example, table 4.1A or 4-1A, sorry, is W sections with your FY equal to 50 KSI. Table 4-1B, 4-1B is W sections with an FY of 65, I think. Yeah, and then 4-1C. So make sure you're in the right table. Right? If I say A992, that's an FY of 50, go to table 4-1A. If we have, I don't know, A913 60, that's an F, no, that's, I want a 65. A913 65, that has a yield stress of 65, use table 4-1B. I don't know why you popped up. So, okay, make sure you're in the right table. And now I'm going to talk about this last part. These tables assume, for W sections, at least, and it even says, see, it says right here, how to calculate an equivalent effective length. So, let's see. I'm going to say it one more time. Table 4-1, A, B, and C assumes that your slenderness ratio in the Y direction is greater than your slenderness ratio about the x-axis or the strong axis. That means weak axis buckling controls. Whatever has the highest slenderness ratio, that's the, right? The more slender, if it's more slender in one direction than the other, the one that it's most slender in is the direction that it's going to buckle first. So those tables assume that it's going to buckle about that y-axis. But if your K and strong axis buckling controls. That means, but if I go to these tables, let's go to these tables and I'll show you what I'm talking about. These tables, like here we're looking at W14s with an FY of 50 KSI. Right, go to table 4-1, the very or any of them, but 4-1A starts on page 4-12. This is a W14 with an FY of 50 KSI, so it's like A992 steel. Then I know my length, my effective length. If I have like an effective length of 20 feet, I know that a W14 by 550 can hold 5,920 kips. But this assumes you're looking at KL with respect to the least radius of gyration, RY. This right here, RY. So I'm using an effective length, LCY. This is equivalent to LCY, or K times LY. So that's what I mean by effective length, KL, with respect to least radius of gyration. But if I know that strong axis buckling controls, I can find an equivalent. And it's right there in the beginning of the chapter too. Calculate an equivalent LCY to use in the table. So let's see. KL over R, let's say I have a LCX over RX. I'm gonna go LCX over RX, right? That's my slenderness ratio. I want to find a length that would have I want to set that equivalent to right. This is my controlling slenderness ratio. I'm going to find what would the length be if it was buckling about the y-axis with the same slenderness ratio. So then all I have to do, solve for that equivalent, LCY equivalent, is my unbraced length in the x direction divided by Rx over Ry. This is an equivalent length, now assuming buckling about the y-axis. So if I find that my slenderness ratio for my x-axis, my KL over R, so my LCX over RX is greater than my LCY over RY, that means I'm going to buckle in about my strong axis before my weak axis. But if I want to use the table, now you could just say, screw this and go back to the spec and calculate it yourself. That's fine. Use the equations. But if you wanted to use the table, all you have to do is divide that effective length in the x direction by the Rx over Ry. Like, let's say, here, let's write a little example. Let's say my KL, my LCX, KLX or LCX, KLX, whatever it is, over RX is 100. And my LCY over RY is 50. That means, maybe because I braced it, and so I have different unbraced lengths. Normally it wouldn't happen, but if I have a longer length, right? If my, let's say my RX is 2 inches. That would mean my LCX is 200 inches, right? My RY is 1 inch. My LCY is 50 inches. That means I braced it 3 times, right, I've cut that 200 inches. I have y-axis bracing along the length. So my unbraced length is so much shorter, and I have a higher slenderness ratio about my strong axis. So a higher slenderness ratio means strong axis buckling controls. So what would be an equivalent that's my LCX divided by RX over RY. So let's see, LCX was 200 inches, RX over RY is 2 inches over 1 inch. So that gives you 100 inches. 200 divided by 2. This means this particular shape will strong axis buckle at, or no. Yeah. Will strong axis buckle at 100 inches, or no, 200 inches long. $200 unbraced, right? And weak axis buckle at 100 inches unbraced. That's what that equivalent means. My unbraced length in my strong axis direction is 200, but my unbraced length in my weak axis is 50. Well, it can be up to 100 before my weak axis starts controlling. So the fact that it's only at 50 means it's not going to buckle in my weak axis. It's going to buckle in my strong axis. So if I want to use the design tables, I need to come up with an equivalent length. And I do that by dividing by the radius of gyration ratio, which is actually in the manual in those tables. And so I say, well, it has to be up to 100 inches to buckle in the weak axis. And I would enter the table with 100 inches to determine BCPN. Which that unbraced length isn't actually an unbraced length that exists in that 100 inches isn't something that's actually, my member doesn't have an unbraced length of 100 inches in the Y direction, it's actually 50. But if I want to use the table, I have to enter with this equivalent, right? In my design table. So, right, if we look down here, right? Because this effective length right here is only the least radius of gyration. They assumed when they made these tables that it was going to buckle about the weak axis. If your weak axis buckling isn't controlling, if your strong axis buckling, way down here is this Rx over Ry ratio. So we'll do some problems, some examples that utilize this so you can see it more in action, but I want you guys to stew on that for a little bit. This is something that trips up a lot of people. So maybe, I hope that example helped of why we have to make this equivalent. We're like, well, it would buckle at the same load if it was unbraced 100 inches in the x-axis, in the y-axis. Okay? So that is actually all of the spec that we are going to use right now. This, you can do design examples, which I'll have some examples worked out, and then we'll do some together. But here is basic compression design for a flexural, assuming flexural buckling controls in a doubly symmetric, non-slender cross section. Okay? Let me know if you have questions.